All right, folks, let's begin. Can you shut your laptops? And if you don't mind, can all of you just move to the first row because there isn't anybody in class and there's no need for me to shout. First or the second row. Can you come up here? Thank you. Aha. All right, let's begin. So we're going to continue. Since we are enjoying this so much and there's so many of us in class, I've actually planned to drag this topic out over 2 more lectures. We're going to continue with Hopfield networks and Boltzmann machines. Here's where we were. This is how we defined a Hopfield network. It's a symmetric, loopy network. Now, symmetry is not that important. Loopiness is. Where each neuron had a threshold activation. It fired if the incoming field was positive, if the output was 1. If the incoming field was negative, the output was a -1. And the way it operated, at each step of the proceedings, the neuron receives a field. If the sign of the field matches the current output, then the neuron doesn't actually change its output because the output matches the field. If the sign of the field is opposed to the output, then the neuron flips. And we saw that this would result in iterative updates to the neurons because each time a neuron aligned itself to the field, it would change the field at other neurons. Those neurons might flip, and now the field of the neuron itself could change, and then the neuron might just flip right back. So these changes, this evolution would continue. And at each step, we saw that we could define this notion of an energy of the network, which is the negative weighted sum of all pairs of neurons, where the weight for any pair was the weight of the edge connecting the two. And this energy was guaranteed to be non-decreasing, more likely to decrease. It was guaranteed to be non-increasing, more likely it would decrease after each evolution. And the network would continue to evolve until the energy hit a local minimum. Now, if I want to write this in vector form, if I want to write the weights as a matrix, then the energy could just be written as minus of y transpose wy, the inner product of y with itself, the matrix and a matrix norm, where y represents the vector of the neuron states, neuron values, right? Activations. And there was also an additional bias term, minus b transpose y, where the b accounts for the bias in the affine terms. But when we thought about it in terms of spin glasses, you could think of it as an external field that was being applied to the network. And we saw that the network would evolve. If you set it in some value like so, each neuron is going to flip to align itself with the local field. And this evolution would continue until the energy of the network, which we defined it in this manner, hit some local minimum beyond which the network would no longer evolve. Because you're guaranteed that any evolution of the network must decrease this energy. So this gave us the notion of a content addressable memory, where each local minimum represented some pattern that the network was storing. And so if you wanted to recall a pattern, then you could set the network in some corrupted version of the pattern. It would evolve till it got to that pattern. Basically, it was recalling patterns by content. You set the network to be approximately equal to the content you wanted to recover, and it would evolve until it recovered that content. So it's a content addressable memory, also called an associative memory. These are the two terms you're likely to encounter. And so we saw some examples of this content addressable memory, where we had this network which was designed to store these two pictures, the Bugs Bunny and the Chip and Dale. If you initialized it with the corrupted version of the Bugs Bunny picture, it would evolve until you got the Bugs Bunny itself. If you erased half the Chip and Dale picture, it would evolve until it gave you back the original picture with some noise. Now, what are these noises? We'll see, right, in a bit. Now, the question was, okay, how do you actually, so we know that the network behaves in this manner, but then how do you actually design the network to store specific patterns in memory? That was the question. Turns out there are three different approaches to doing this. The first, which was originally proposed, was the Hebbian learning approach. The second, which we briefly looked at, was the geometric approach, and we spent some time looking at both of these in the last class, and it was all very confusing because it is confusing. These are not very nicely analyzable. The third approach is based on optimization. Now, these are mechanisms for making the network store specific patterns, but there's also the question of how many patterns can the network store? So for the Hebbian learning approach, we saw that if you wanted to store a specific pattern, then you can just set the weight matrix to be the outer product of the pattern by itself, with a diagonal term set to 0. Even if you don't set the diagonal terms to 0, that weight matrix is going to still be a perfectly reasonable weight matrix to recover that specific pattern. But this works for one pattern. What happens when we try to store multiple patterns? Then you can design your weight matrix to be proportional to the sum of the outer products of the patterns that you're trying to store, all of the patterns that you're trying to store. This was the standard Hebbian learning framework, right? And we saw that if you use this mechanism, then with a probability of 0.004 or 0.996 of success, you could store up to 0.14 n random patterns in the network. If you're willing to tolerate a lower probability of success, then you can store more. But we also found that there's something funny about this. This analysis only works for random patterns. More generally, we found that in many cases, you can actually store more than 0.14 n patterns, in others you cannot. And analyzing the behavior was kind of tedious. So that was the Hebbian learning approach. There was a second way of looking at the whole thing. This was in terms of linear algebra. This was the geometric approach, where we saw that if I think of each pattern as some vector in the space, w times y is simply going to rotate the vector and change the length. So then when you take the sign, it is snapping the vector back to the closest corner. And once I realize this, then I can say that a pattern is stored, at least it's stationary, if sine of wy equals y, right? And we just want to design w such that this holds. Now, clearly, the obvious thing to do is that we can just say that the y's are the eigenvectors of w, the y's that you're trying to store. And if you designed your w in this manner, then every one of the y's is actually going to be stationary. But for this to work, all of the vectors have to be orthogonal to one another. Now, but this also gave us an extra piece of information. And the extra piece of information, if I can find a chalk, is this, that since you're looking for sine of wy equals y, right? How many such patterns can you, or in the limit, you want to get wy equals y, right? How many such patterns can you have? Anyone? That's going to be the rank of the matrix, right? Which is going to be the number of neurons in the network. That's a standard linear algebra. A matrix W is going to have as many eigenvectors as the size of the matrix itself, right? The dimensionality of the matrix. And so from this, we can sort of come to the conclusion that we're really trying to design W such that WY, the sign of WY is the same as Y for the patterns you're trying to store. And the way you can design it is, just look at the eigenanalysis. If all of your patterns are orthogonal, you can make the patterns the eigenvectors of your matrix. And if the corresponding eigenvalues are 1, that gave you the Hebbian learning rule, right? But there was a consequence of this, that first, you can't store more than n orthogonal patterns intentionally. But second, even if these patterns are stationary, any linear combination of these patterns is also going to be stationary. So if you have a binary pattern, which is a linear combination of all of these patterns, then those binary patterns are also stationary, which is kind of unpleasant, right? It's not something that you really want. So, and if the patterns are non-orthogonal, if you still use the Hebbian learning rule, you have to work harder at trying to analyze what's happening. But at the end of the day, there was a take-home lesson from this, that you can hope to store maybe order n patterns for an n-size network if you use these Hebbian principles or the geometric principles for learning. But even so, trying to figure out how the entire thing works is kind of hard. And if your patterns are not orthogonal, analyzing this is basically an NP hard problem. So all very fine. The bottom line of all of the very complicated looking math was that with a network of n units, you can get an exponential and n number of stationary patterns, but of these maybe n were something that you stored intentionally, and the rest were parasitic memories, right? Things that just happened to be stationary or even had little attractors. So there's another result, that if I have a specific set of k patterns, I can always, where k is lesser than or equal to n, regardless of what these patterns are, I can always build a network for which these patterns are not only stationary, they might even be stable. So where does that network come from? For that, first, how do we find the network? Number one. But then the second question is, when I'm trying to store these patterns, I get all of these spurious parasitic memories, things that I don't want to store. How do I minimize this, right? That gives us the real solution, which is based on optimization, which is what we should have jumped to first, but then it's useful to look at the background to get an idea of what the real problem is. And so let's go back. I have this, now, I have this energy function, and we know that a stationary pattern is one where the energy function is locally flat, right? And in fact, a stable pattern is one where the energy function is a local minimum, right? So given this, if I asked you to design the W, and this is how I set up my network, right? So I have the W and the B. These are the parameters that I have control over. And now if I roll the problem over to you and say, here is a pattern Y, I want this network to be stable and stationary at that particular pattern. How would you go about composing the network?
Differentiate E with respect to W.
And yes, so you want to minimize E with respect to W for the given Y, right? What if I gave you multiple Ys?
We just create a matrix and then do this thing.
Yeah, but then that's going to give you one minimum, right? I want each of the Ys to be a minimum. What would I do?
Average?
Average. You're kind of getting there, but then I can say this, make the statement like so, right? Estimate W and B such that E is minimized for the set of patterns I want to store, right? But I want it to be, I don't want it parasitic memories. I want those to be stationary, right? Stable. E is not minimum for the remaining Ys, right? I can restate the problem like this, right? If I give you this as my statement, what would you do? How would you address this? It's obvious, guys. We've been doing this all semester long, right? I want to minimize the total energy of all of my target patterns. At each of the target patterns, I want the energy to be minimized, correct? And if I just do this, is this enough? Firstly, will this solve the, is this a good thing to be doing? Shani, can you say that, speak up? Thank you. Right? Maximize the total energy on all the other patterns. Right? This is all I really want to do. And this is the objective function that I'm going to be optimizing. Make sense? You can even trade off how important it is to minimize the energy at these patterns and how unimportant it is to maximize the energy elsewhere. But this is we can set up an objective function, and now we can design my network to minimize this objective function. How would I minimize this objective function? Guys?
Gradient descent.
Thank you, right? I can take a simple gradient descent. And if I take the derivative of this with respect to W, then the energy for any y is minus half of y transpose wy, correct? So if I take the derivative of y transpose wy with respect to W, that just ends up being y transpose. We've seen this in the class. So this means that the derivative of this term with respect to W is the sum of the outer products of the y's for all of the y's that I'm trying to store. And the second term is going to be the same term summed over all the patterns that I'm not trying to store. I'm trying not to store. That's being subtracted. How does this differ from the Hebbian learning rule? What was the Hebbian learning rule missing?
Eta and W.
Well, eta maybe, but the more important thing was the Hebbian learning rule was using just the first term. It was missing the second term. It was pulling down the energy at the patterns that you were trying to store, but it didn't really know what was happening to the other patterns. Those might have gotten even lower still, right? We want to explicitly push up the energy at those patterns, right? Yeah.
How do we get those non-target patterns?
There are an exponential number of them, correct? You'd have to consider all of them. Not really. That was a very good question. The rest of the lecture is answering your question. Okay. So this guy is the sum over all of the target patterns that I'm trying to store. But then when I'm summing it, I can emphasize some patterns more than others by presenting them multiple times, right? So I can say it's more important to remember this guy than it is to remember this guy. And this second term, how many of these do I need to store? Do I need to include all of these? That's to answer your question, right? So are they all equally important? Let me draw this again. This is going to be your standard energy contour for any setting of W, right? And you may have some patterns that you're trying to store. You want to modify the W, and modifying the W is going to change the energy contour, correct? Such that the energy at these yellow dots is pulled down. You want to minimize the energy at the target patterns that you're trying to store. And you want to increase the energy everywhere else so that each of these patterns ends up in a bowl, right? Once you visualize things like this, things become easier to understand. Do you really need to consider every combination in the second term? Yes or no? So what can you use? Basically, you can just pull up all the values, right? So at every pass, I find all the values, I pull them up. If I keep pulling up the values and I keep pushing down the target patterns, eventually there's going to be no valley which is not the target pattern. And the values are going to be far fewer in number than the entire thing, right? So If you raise every valley, eventually they'll all move up above the target patterns and many will even vanish. So you're going to end up with the problem you have. The network that only stores the target patterns. But then what's the problem with this? Finding the valleys. How can you find the valleys?
Calculate where gradient is 0.
Where the gradients, again, that's going to be hard to find, right? You're going to have to be solving a problem, but yeah, Chakra?
Same whatever you said, that current local minimum.
Current local, here is what I can do, right? How do you identify all the valleys? I'm just going to keep initializing the network randomly and let it evolve. If I let it evolve, where is it going to settle down? In valleys, correct? And so I can just do this. I can initialize my W, and then I can compute the outer product for all the target patterns. And if I use them on the first term, it's going to be pushing down the energy at the target patterns. The second term, which has an exponential of the number of contributors in the worst case, if you're being naive about it, that's where we are going to do something different. We are going to randomly initialize the network several times and let it evolve and settle at a value. And then you're going to pick all of these guys and you would pull the energy at those places up. Those are going to go into the second term. Right? Make sense to everybody? Yeah. So this is what your learning algorithm would be. You're going to initialize W, and then until it, until the whole thing converges or you're bored or you run out of compute, you would you can either do this in batch mode, compute this term over all your target patterns, then run several simulations where you initialize the network randomly, let it evolve, and then find all the valleys, find the second term, and use the difference between the two as your gradient. Or you can do the SGD variant, right? You pull up one target pattern, and that target pattern is going to be used here. Then secondly, you're going to just randomly initialize your network and let it evolve till it gets to a valley. That's going to be the second term over here. The difference between the two is what you're going to be. The difference between these two outer products is the gradient that you'd be using to update your weights. So everyone with me so far? Make sense, Eric? Right. So this is easy, right? Once you begin thinking about things this way, the whole problem becomes a lot more tractable. But then now you can think ahead. Do you really want to randomly pull up valleys? Or is there something smarter you can do? If we go and look at this picture, which are the valleys that are important? Pardon me? The ones nearby the target, right? Something that's far away is irrelevant to me. So what I will do is, instead of randomly initializing the network and letting it evolve, not all valleys are equally important. We really want the memories to be stable, right? Which means you want the individual memories to be in valleys. The valleys near the memories must be pulled up, right? Spurious, those are more important to eliminate. This valley, you don't really care, this is too far. These are the valleys that you want to eliminate, right? Now, given this, how would you update the algorithm that we just used?
Initialize with the white piece.
Thank you, right? Initialize the network, add the valid memories, and then let it evolve. And then it's going to roll down into the nearest valley, right? And that is what you're going to update, right? And so, again, if I'm training the network, what I would do if I were doing this in batch mode, I would have the current estimate of W. Then at each target pattern, I'd just let the network evolve till it's settled down. And so the second term is going to be computed only using this valleys adjacent to the target pattern, and the first term is only going to consider all of the target patterns. And again, if I want to do the SGD version of this, then what I would do is at each iteration, I'd sample one of the target patterns, then initialize the network there and let it evolve till it went to a valley, and then look at the difference in the two outer products. That's going to be the gradient that I'm going to use to update it. Yeah.
In some of the earlier pictures, you showed the parasitic memories as like little dips.
Yeah.
Doesn't this fail to capture this?
This doesn't, right? You're still, but what happens is if you keep doing this long enough, the bowls around the memories are going to be wide enough. And the assumption is that things that are far away from a valid memory is something that maybe that they're not really interested in. It doesn't completely ignore it eliminates parasitic memories close to your target, but not the ones that are far away.
Are you only sampling at the patterns or are you sampling around them?
So you're picking the pattern there, and then that pattern has to be a minimum, right? So what will happen is you will find that at each of these patterns, there is no further evolution which moves things down. So at least in a small region around the patterns, you won't have these parasitic memories, right? But that's again a very good point. We will answer that question. One step at a time. Good question, right? But before that, what if there's another target pattern downstream? If I let this evolve, and it evolves until it hits the other target pattern, something that was supposed to go down is now going up, right? How can you fix that? Take the midpoint. You don't know that there's another pattern down there, right? So something like this. Here's what I can do. There's no need for me to raise the entire surface or even the entire, even every valley. I just need to raise the neighborhood of every target pattern. I might say, for example, that I want to be able to correct up to 10 errors, right? So then I would let it evolve for only 10 steps and pull that up. So it makes sure that each pattern is in a local valley, and that's about it. So you don't necessarily need to let it evolve till it hits a valley. You let it evolve until it hits the limit of whatever it is you want the recall to be, right? And then you would pull this thing up. So starting from the target pattern, let the network evolve only a few steps. Then try to raise the resultant location. That making sense? Right? And this is going to evolve it's going to sort of avoid the problem of down valley targets, and it will raise the neighborhood of the target. And so this is what your updated algorithm is going to be. So as you work through this optimization one step at a time, each step is a logical development from the previous step. If I just gave you the final solution, maybe it won't make that much sense, but as you keep working through this, you can see how each step is a logical extension. So what I would do now is that I'd initialize YP and then just let it evolve only a few steps. That's going to give me a target pattern, maybe that far out. I'll pull that up, this one goes down. So this would be your training algorithm, right? Now, so the story so far, Hopfield nets with n neurons can store up to 0.14 n random patterns. And the problem with Hebbian learning is that Hebbian learning has a fundamental problem. It's only pulling down the energy of the target patterns. It's not dealing with the non-target patterns, so it may not actually give you what you want. Once you write things in this manner, that became obvious. When we were just looking at Hebbian learning all by itself, it wasn't very obvious, right? Second, in theory, the number of intentionally stored patterns can be as large as n, but they come with parasitic memories. You don't worry about parasitic memories which are very far away, but something that's in the vicinity is a bad thing. And so when you saw that little example with the Bugs Bunny, when you recalled it, there were lots of little dots in the picture. That was a little dip that was close to Bugs Bunny. So it still looked like Bugs Bunny, but then you had all of those little bits of noise. That's the kind of thing that you would really like to avoid, right? And so this kind of network can be stored through optimization by minimizing the energy of the target patterns while increasing the energy of the neighboring patterns. Questions? Any? No. Okay. So, all right. We figured out a mechanism for creating a network that can store n patterns, up to n patterns, right? And if I have n neurons, I can store n patterns. Or even if it's not n, even if it's n squared, it's a function of n, right? But suppose I want to train a network, my pictures, but this has a limitation. So if I have an n pixel picture, I can only store up to n or order n or some function of n pixel pictures. But the number of things I want to store doesn't have to necessarily relate to the size of the thing I'm trying to store, correct? So given that I don't necessarily want to store, it doesn't make sense for me to limit the number of things I store by the size of the thing I store. How can you modify this approach to store more than n patterns? Get creative. I'll give you a few minutes. Anyone? All right, if I gave you the problem, what would you do? So here's the thing. The number of patterns I can store is related to the size of the pattern I can store, right? So what can I do? Because that is going to be the size of my network. Pardon me?
Store it in parts.
If I store it in parts, I'm going to store even smaller things, right? The number of things I can store is going to be even smaller. So what can I do? But you're in the right direction. Pardon me? If I merge two patterns, it's still going to, then I'm going to have a fewer number of patterns. You're reducing the number of things you're storing, right?
Find a way to reuse certain pixels or certain patterns.
Find a way to reuse, but this is a mathematical restriction, right?
Like a dynamic programming approach, it keeps storing.
Okay, still, it hasn't addressed the basic problem. So this is where genius comes in, right? The answer stares you in the face, but you don't see it. What I will do, how can I, the information capacity of the network, the proof is that it's order n cubed, but it's still a function of n. I want to increase this. And so what will I do? I'm going to patch a bunch of junk bits. I have n-bit patterns. I add to it some k additional bits. Those bits I'm not interested in, but now the actual pattern size is n plus k. And whatever I'm going to try to store is now a function of n plus k, right? And so here's what I would do. Instead of storing, say, 2-bit patterns, I store 4-bit patterns. And now I can store my patterns. When I'm recalling things, I initialize the network, I let it come to the valley, I only read the first 2 bits. I throw away the last 2 bits. So, that make sense?
Pixelation or something.
No, I literally just patch things at the end, right? So if I'm trying to store 2 bits, I add to it 6 extra bits.
They're not part of the weight calculation.
They're all part of the weight calculation. So the point is now, instead of storing this 2-bit pattern, I'm going to be storing this 6-bit pattern.
So what's the difference between increasing the number of neurons instead of just patching up?
So here, the way we did it, each neuron was a pixel, right? So this is going to end up resulting with an increased number of neurons because of the manner in which we design the network, right? And so you add a large number of neurons whose values you don't care about, which is the same as saying I'm going to be patching a whole bunch of bits, but I don't care about those bits, right? And so now the new capacity is going to be n plus k, or function of n plus k. If the information capacity is n cubed, then with 2 bits, I could store maybe 8 patterns. Actually can't 8, but order n cube is the, but with 6 bits, I'm going to be, my capacity is 6 cubed, right? That's the, actually it's going to be 6, but still you can store up to 6 patterns, right? So you only care about the pattern of the first 10 neurons. We are interested in n-bit patterns. The rest of them are there only to increase the capacity of the network. And so I can think of this as two different subcomponents. When I build my network, I can think of the bits that represent the patterns, the bits that I'm trying to recover, as my visible neurons, and the neurons corresponding to the bits that I'm not interested in as my hidden neurons. The neurons that store the actual patterns of interest are just the visible neurons. And these guys only serve to increase the capacity of the network. These are my hidden neurons. And these can be set to anything to store a visible pattern, right? So physically, if I've got n bits and I'm trying to store an n-bit pattern, store n-bit patterns, what I will do over here is patch a whole bunch of hidden bits to make it n plus k. And now these are these additional k bits are my don't care bits. I don't care what value they take. I can fill them with anything, right? But now the capacity of the network becomes a function of n plus k rather than n. It's much greater than just order n. So I can store much more. And now we can store n plus k patterns, a function of n plus k patterns. So, but then what do those, I'm starting off with these n bits. I'm expanding it to n plus k bits. What must those k bits be? Right? I want to store a 1, 0. But then I've passed an additional 6 bits. What are those 6 bits? Are they, I mean, I'm trying to store a 1 minus 1. I've patched an additional 6 bits. What must those 6 bits be? I have to fill something, right? I'm expanding this pattern. And how you fill it up and how you extend the visible pattern to account for the don't care bits ends up being interesting. Now, one simple option is I can just flip a coin. I'm just extending it. I can extend it any odd how, right? I can fill this up randomly. Here's what more I can do. If I'm trying to store 1, 0, right? I'm creating a 6-bit network. Why do I need to keep only one copy of the 1, 0? I can make multiple copies, each with its own value, right? And so it becomes easier for those things to be recalled. And then how do I store them? I store these things. The standard optimization-based framework should just do the job, right? So this is for storage. And then during recall, how do I retrieve a memory? The usual evolution mechanism. I initialize the network, I let it evolve, and it's going to pull up the memory of interest. But then here is an interesting thing, that I could now, during the recall, the junk bits, the don't care bits that you set, are going to have a say in what you're going to recall. And that's something you'd have to begin worrying about, right? Because it's the extended pattern that you're recalling. But then the key sort of counteracting the fact that those guys do have an influence is the fact that if you make an error in recalling the junk bits, you don't care. You're only interested in recalling the visible bits properly, right? So here's what we end up with. If you're going to have an n visible bits, you're going to have some k hidden bits. And the value taken by the k hidden neurons during recall doesn't really matter, even if that value doesn't match what we originally tried to store. So can I somehow take advantage of this? Also, we all have the situation that I can have multiple extended patterns, right? The guy to the right. And so can I have the fact that I can have multiple extended patterns with the same pattern over visible bits? Can I somehow take advantage of this? Can I exploit this somehow? Let's see how we can. Now, the question comes down to what do I set these don't care bits to be when I'm trying to store a pattern? Simply randomly flipping a coin should kind of work, but it's not the best thing you can do, right? It doesn't exploit the redundancy, the fact that errors over there don't really matter. It also doesn't exploit the fact that those guys are going to eventually guide the recall of the visible bits also. Because when you are trying to recall something, the network may end up focusing on getting the don't care bits right at the cost of the visible bits. And that's something you have to worry about as well, right? And so it's possible to say, so we want to say, how do I set these don't care bits such that the longer pattern is somehow more memorable? If my don't care bits, so for example, if I take 2 bits and I expand it to 18 bits, and I have 2 very distinct 2-bit patterns, but the resulting 18-bit patterns are very close, then they're going to be confusable, right? So somehow we want to make sure that these extended patterns are individually more memorable, that they are more distant from one another somehow. So it's possible to set the don't care bits such that the overall pattern is somehow more memorable, but it's also possible to have multiple extended patterns, which for the same visible bits. So what this means is that if I have, say, these many visible bits, then I can have these additional hidden bits. And then you have 2 kinds of conditions. One is where both of these represent the same visible bit pattern. The other is where I have something like this. And this entire range over here basically just represents different variations on the don't care patterns, but have the same visible patterns. So there are different ways of sort of setting these invisible bits. And all of these possibilities can be exploited. But then how do we exploit those? To exploit them properly, we have to sort of view the Hopfield network somewhat differently. Now, when I began talking about Hopfield networks in the last class, I told you that this was actually a generative model, right? It's a probabilistic model. So where does that come from? For a binary y, I can say, now here's something that's very common. Why do we like Gaussian probability distributions when we are dealing with real vectors? The reason we like Gaussian probability distributions, quite apart from the fact that nature tends to like Gaussian, is that when you think of the log of a Gaussian, it's a quadratic. Quadratics relate to energy. And so a Gaussian basically is a probability distribution that was obtained by taking an energy function and exponentiating it, right? So anytime you have an objective function and you want to make it a probabilistic statement, one way to think about it is, say, I take this objective function and exponentiate it. I can call my objective function the log of that exponentiated term. If the exponentiated term is properly normalized, it becomes a probability distribution. Voila. I have a probabilistic model. So that is the relationship that we actually have very often in these exponential models. So here's what I can say or do. I can say that I can define a probability distribution of this kind, which is some e raised to, so minus of the energy is what we wanted to minimize, right? So, or I can define, this is e raised to this guy, e raised to the energy as my probability distribution, and in which case I can say minimizing the negative energy, minimizing the energy is the same as maximizing my log likelihood. There's a minus, the minus should go, there is, yeah. So minimizing my energy is the same as maximizing this probability, right? So this, what was a minimization of a energy became a maximization of a probability. And now I can say the entire network basically represents draws from this guy. So minimum is the most likely value, right? And so now, when I think of it this way, something interesting pops out. Now we'll see that this is not completely ad hoc, that this actually comes out of some physical principles. But before that, think about it this way, right? When I was trying to minimize this term to optimize my weights, this was the sum of the energies of the target patterns minus the sum of the energies of the non-target patterns. Alternately, I can think of it as the weighted sum of the energies of the target patterns minus the weighted sum of the energies of the non-target patterns. And so when I take a derivative, you're going to end up with something like this, right? Where this is the weighted sum of the outer products of the target patterns. This is the weighted sum of the derivatives for the outer products for the non-target patterns. And this weight you can think of as the relative importance of each pattern. Something that's more important is going to get more weight, right? And if I say furthermore that, so I can say this can be used to give more importance to frequently presented memories, and this beta can be used to give more importance to more attractive spurious memories. You want to make sure that they get kicked up in the energy contour. If those guys actually sum to 1, the weights, this begins looking like an expectation, right? It's basically saying it's the expected value of the outer products of the target patterns minus the expected value of the outer product of the non-target patterns. Or more generally, I can think of it somewhat differently. If these guys over here are the patterns that you've drawn from real life, then the weight over here is going to give you how frequently each pattern was seen, right? So the first term is the expected value of the outer product of patterns drawn from a real life distribution. And the second term is the expected value of patterns drawn from the synthetic distribution that the model is representing. And you're trying to minimize the difference between the two, thereby making sure that the model actually ends up giving you the same expectations as the real world data itself. So I can think of this way, that the first term is the expectation of the outer product of y's drawn from real life, from the true distribution of the patterns that you're trying to remember, right? And the second term is the expected value of the outer product of the patterns drawn from the distribution represented by the network. And specifically in our case, the network represents is represented by Boltzmann distribution, right? And if the gap is minimized, then you're going to say that the network represents the distribution of true life. So the behavior of the Hopfield network over here, once I begin looking at it in terms of weighted sums, which is a perfectly natural thing to do, it begins to look like some kind of a probabilistic optimization, right? Now let's go back and see where this interpretation comes from. The behavior of the Hopfield network is analogous to the annealed dynamics of a spin glass. We talked about spin glasses in the last class. And that is characterized by a Boltzmann distribution. So we're going to explicitly model the Hopfield network as a distribution. But then, where did that come from? Let's go back and think about the spin glasses. What did we say about spin glasses? That you have this dielectric medium, you have lots of dipoles. Each dipole is trying to align itself to the local field, and then it's going to stay there, right, once it evolves. But is that really what's happening? If it has evolved, is a dipole going to stay at that configuration where everything is stable? Is that what happens in real life? What do we know about physics? What is the only time at which a system doesn't change at all?
0K.
0 Kelvin, right? At any other temperature, it's actually always bouncing around. And so the system is never actually in one specific state. What is happening is that when I set the system up, it's always continuously changing. But so what is the evolution happening over here? The probability with which different states are visited, different configurations are visited, that changes. And exactly how does that change? Here's what happens, right? A thermodynamic system at temperature T can exist in one of many states, right? It has n dipoles, it can exist in 1 of 2 raised to n possible states. But then at any time, the probability of finding the system in a specific state S is going to be some PT of S. It depends on the temperature. Okay? And we also saw that each state has a potential energy. Now, the internal energy of the system representing its capacity to do work is the average potential energy. So what is the probability with which it's in state S times what is the energy of S? You take the average over all possible states. This is how much it's capable of doing work. But then there's something that kind of interferes with the ability of the system to do work. And that has to do with temperature. When something is hot, it's not going to be well behaved. It's going to be bouncing around, right? And so that interferes. That is the entropy. This capacity to do work is counteracted by the internal disorder of the system, which is the thermodynamic principle of entropy, where entropy is given by minus P log P. We know the formula for entropy, right? And so the Helmholtz free energy of the system combines these two terms. The expected energy of all the states that the system can visit plus the entropy of the system. And so when you just let the system cool, if you set the system at some temperature and just let it be, what it's going to do is it's going to keep flipping between different states. But the probability with which it visits the different states keeps changing. And eventually, after a long time, it's going to be settling down over some probability distribution over the states. And that is the stable system, right? That's where it stabilizes. So it's not like it's going to stop at one state. What you will have is that if I have all of these as my states, you're going to have some probability distribution initially. Then you just keep the system at the same temperature, just let it stay. And eventually it's going to keep changing and changing, and maybe it settles down into something like this, right? The probability distribution over the states changes, and the specific probability distribution it's going to arrive at depends on two things: the energy of the different states and the temperature. But it's going to do this to minimize, remember, it always wants to minimize the total energy of the system, right? So it's going to do this to minimize the Helmholtz free energy. So what it will actually do is, that's your Helmholtz free energy. A system held at a specific temperature anneals by varying the rate at which it visits the different states until this energy is minimized. This is the standard potential energy minimization principle that we're all aware of, right? Now, if I write things this way, what is the value? What is the variable over here? The variable is the probability with which it visits the different states, PT of S, right? So let's find the PT of S where this guy is minimum. If I write that down, what will I find? I want to say dft over dpt of S equals 0. Standard minimization technique, right? And what is that? That's going to be for any particular S. So df over dpt of S for a specific S is going to be Es from the first term. And from the second term, it's going to be minus K is the Boltzmann constant. So the Helmholtz free energy is, again, it's the entropy times the temperature times the Boltzmann constant. That's the disorder term. That's where the Boltzmann thing came in. And the first term is the average for potential energy over all states, right? So the second one is going to be minus KT times 1 plus log P, right? To 0. That make sense? Right? There's an extra term that I'm ignoring over here. All of the probabilities must sum to 1. But if I ignore that for the moment, I can say log of PT of S is going to be some constant times, for now it's going to be minus of E of S minus kt, is it plus kt? Is that the correct one? Or that goes on the other side. Actually, it's going to be ES minus kt, right? Is that what I will get? Because I'm moving the log on the other side. So implies Pt of S is proportional to e raised to energy of S divided by something, right? It's proportional. But the kT is not a function of the energy, right? And so if you actually see this, then obviously this is a probability. So this implies Pt of S equals 1 over some z times e raised to E of S. Is that coming out right? I'm just minimizing that with respect to the energy, right? The probability. And okay, over kT, right? I'm missing the kT. There was a kT here minus 1. I think that's what I'm missing. Yeah, and that's going to be e raised to over kT. And so I have some loss of the sign, but you get the idea. That's where the Boltzmann distribution comes from, right? The Boltzmann distribution is the distribution over the probability distribution over states, where the system settles down at any temperature T if you just let the system evolve. And now observe that when T goes down to 0, absolute 0, then the system then the specific state which has the lowest energy is going to have all of the probability, and all the other states are going to have probability 0. So only at absolute 0 will the system settle at the lowest energy state. Otherwise, all that happens is that the lowest energy state is going to be more probable than other states, but it's going to have a distribution over all states, right? So using this principle, this is the Boltzmann distribution or the Gibbs distribution. You have z is a normalizing constant. Note the dependence on t. At t equals 0, the system always remains at the lowest energy configuration with p equals 1. But any other temperature, the system is actually not stable. It's going to be just bouncing around between states. The probability distribution of states evolves if you just keep it at that temperature till it arrives at the Gibbs distribution, right? And so here, when I define my energy in this manner, e raised to minus E of S, that's the Gibbs distribution, because our Hopfield network was basically the computational equivalent of the spin glass, right? And the denominator term is basically summing e raised to minus ES over all possible states. The only reason for doing that is that the entire thing has to be a probability distribution which sums to 1. So the denominator term is just summing to 1, okay? And so if I defined things in this manner, if I redefined my Hopfield network exactly like a spin glass and said that at any time it's not going to be at a deterministic state, the states are probabilistic, but the probability distribution over states follows a Gibbs distribution. So I've taken the behavior at 0 Kelvin and moved it up to the behavior at say 1 Kelvin, right? Basically. So slightly raised temperature. So then the neurons are now stochastic and there is disorder, right? It's not going to be at one state, it's going to keep bouncing around, but you have a probability distribution over states. And this is the probability distribution over states at equilibrium when the system is stable, okay? So this is what we call a stochastic Hopfield network. It's a probability distribution over states where the state is a binary string. Specifically, it models a Boltzmann distribution, and the parameters of the model are the weights of the network. So the probability that at equilibrium the network will be in any state is P of S. And now if I somehow let the system operate according to this probability distribution, then once it has settled down, if I pull a random sample, that random sample, if I take a random snapshot, that random snapshot is going to be a sample from the distribution P of S, right? Which in turn is a function of the weights. That making sense to all of you guys, right? We haven't done anything fancy, we just made it more stochastic. But then there's something very pretty that falls out of all of this. We keep talking about the logistic function, right? And the softmax. Where did those come from? It turns out they fall out of exactly this assumption about a network. And if you're wondering how, here is how it is. Now, consider a network, say of 5 neurons, right? For my example. And let's consider 2 states, one where this neuron is 1 and the other where the neuron is -1. So the other 4 neurons are the same. The difference between these two is, in this case it's 1, and in the other case this neuron is -1, right? What is the preference of the system for the one state versus the other? How much does the system prefer this guy versus how much does the system prefer this guy? For this, now let's consider the probability of this state where this state is where that neuron is 1, given all the other neurons, right? Given everything else, given Sj not equal to I. And let's compare this to the probability of the state equals -1 given Sj not equal to I. If I do this, now this one, let's consider the difference between the log probabilities of the two. So if I take the log probability of this setting and minus the log probability of this setting, right? That's going to be the log of P of Si equals 1 minus log of P of Si equals -1. Now the subtracting a log is like, the log of, by putting it equivalent to having that term in the denominator, right? So this is the same as log of P of Si equals 1 given Sj not equal to I, divided by P of Si equals -1 given Sj not equal to I. But then the P of Si equals -1 is the same as 1 minus P of Si equals 1, right? So we haven't done anything complicated yet. I'm just looking at the log of the ratio of the probabilities of the two systems, okay? But then what is this term? What is log of P of S minus log of P of S prime, where this is S and this is S prime? Now, we know that log of P of S is going to be what? What is the probability of any state? It was e raised to the energy times some constant, right? So it's going to be log of e raised to what was it?
S energy by kT.
Yeah, we're not, for the Boltzmann machine, for this Hopfield network, we're ignoring kT times some constant, right? Which is E of S plus C. And log of P of S prime, it's minus energy, correct? Minus E of S is simply going to be minus of ESS prime plus constant. You guys, everybody with me so far? Right? And what was E of S? If I write down E of S, let me write this here. So E of S was simply the summation of Ij, Wij, Si, Sj, right? Plus Bsi, correct? Summation over I. This is what we had, right? So when I write this, I can break this down into two things. These guys, the contribution of everything else, plus the contribution of this one term, right? So this I can decompose this as summation over J Si times W Ji Sj. That's just the contribution of this one, that's this guy, plus the contribution of the others, which I'm just writing as an O, right? Plus B times Si. Now, when I write it this way, there are two distinctions. One is when Si equals 1. When Si equals 1, this is simply W Ji Sj plus B. And when Si is minus 1, it's some minus W Ji Sj plus B. And both of them will have this O term. Right? Everybody with me so far? And so when I take the log, the difference between these two log probabilities, these O's will cancel out because they are common for both. And so all you're going to be left with is going to be this term over here, which is, there's a half. Don't forget the half. I keep forgetting the half, right? Which is summation Wji B Sj plus the bias term. Everyone with me so far? Right? And now I can solve this. I'm just getting log of I'm being somewhat careless, but then I can say log of P of S over 1 minus P of S equals summation J Wji Sj plus Bi. I can solve for P of S. So alternately, I can say P of S over 1 minus P of S equals e raised to summation Wji Sj plus Bi, right? And so what will P of S end up being? It just ends up being your logistic. So when you work through this, the Boltzmann machine tells you that the probability that any neuron will take the value 1 is the logistic computed at that neuron. Right? It looked very complicated. When you erased everything, you ended up with a very familiar formula. And so now you have a very nice thing, right? I'm just going to say that for any neuron, the probability that the neuron is going to take the value 1 is simply the logistic computed at that neuron. Right? So now each neuron is a stochastic unit with a binary state which can take value 0 or 1 that depends on the local field. And at this point, you can convert the whole thing into a probabilistic machine. Here's how you would do it. The conditional distribution of the individual bits in the sequence is a logistic. And so if I want to let this network evolve like a spin glass model, when I converted this deterministic Hopfield network into something stochastic, here's what I would do. I'd initialize all of the neurons, but then instead of just letting each neuron evolve exactly as it was doing before, instead of just saying that each neuron is going to align itself with the local field, which is what we were doing with the standard Hopfield network, right? Instead, at each neuron, I'm going to compute this probability 1 over 1 plus e raised to minus zi. And I'm going to decide, I'm going to flip a coin with that probability of heads to decide if it's going to become a +1 or a -1, right? And just keep letting the network evolve. And if I let the network evolve, eventually it's going to settle down into a Boltzmann distribution. And if I draw a sample from that network, it's going to give me a sample from this Boltzmann distribution. So we'll finish this class early. It'll take me another 20 minutes to talk about Boltzmann distributions. I thought I'd finish this early and I'd take only a very brief class on Monday. So let you off early and we'll have a guest lecture on Wednesday, right? But then here is the nice thing over here. If I replace this energy in the Boltzmann distribution by, instead of saying E of S, I make it Et of S, which is E of S over T. If I so if I actually add in a temperature factor, then this is like saying the temperature is 1, right? But then I can let the temperature go down to 0 slowly, and that's going to give you your standard Hopfield network. But then what is the benefit over here? The point is, in your standard Hopfield network, if you started off at some point, you are always going down towards the lower energy term. Here, depending on the value of t, there's always some probability that you can go the other way, right? Because if the logistic value is close to 0.5, you don't care which way you're going. If the logistic value is close to 1, you're always going to be going down, right? And so suppose you find yourself in a situation where you're like this. You don't want to be stuck over here. So the evolution of this network gives you a non-zero probability that you can actually come out of the local noise and then continue evolving towards a global minimum or the big valley nearby. And so it actually gives you a mechanism for escaping from noise. But then you have to worry about it. This is probabilistic, right? Because this is probabilistic, if I let the network evolve, it's never going to be over here. It's going to keep bouncing around because the network is stochastic, right? So if it's bouncing around, how do I deal with this? How do I actually take a real reading? Anyone? All right.
And you can sample from it.
So what?
You can see one of them.
So what you can do is let it evolve many times and take the average. That is one, right? The other is to say, I'm going to use this mechanism and then slowly drive t to 0. And if t becomes 0, then you know that's going to actually settle at the bottom. That's what annealing is all about, right? So at higher t, it can escape from these little noise valleys. And then as t goes down, it's going to stop bouncing around and stay at one point. And then you get a global minimum. So a lot of the things that we've done in machine learning, annealing, simulated annealing, and all of these other techniques actually derived from this principle over here that we just saw, where you take something that's a standard energy minimization and then convert it to a stochastic process, which actually models the behavior of physical materials, and at the temperature go to 0. The original paper for this, believe it or not, was not in a computer science journal, or it was actually in chemical engineering. The paper by Metropolis in 1953, I think. So you're looking at old stuff. Anyway, stop here, stop early. We'll continue the next class. Hopefully there'll be 5 people at least in the next class. If there aren't, I have 2 choices. I might decide that that is the only class when I'm actually taking the roll call and use that as representing the entire semester, or just not care. I'm going to flip a coin. Yes.